So we're gonna just do this problem. So if you remember where we left off last Monday, we were doing confidence interval for the population mean. And we were doing this when pretty much we don't know what sigma was. So if I don't know what sigma is, you're just gonna be using the t distribution. All right. So we're still continuing on. We're still doing confidence interval for the mean, and we're still doing confidence interval for the mean when population standard deviation is unknown to us. So let's go ahead and do this first problem. So for this first problem, it says the following data represent the age in weeks at which baby first crawl based on a survey of 12 mothers conducted by an essential baby. All right. So if you look right here, we have our data set. So we have one baby that took 52 weeks to crawl, 30 weeks, 44 weeks, all the way to 28 weeks. So that's what the data representing is represent how long did the baby take in order for it to first crawl. All right. Everybody go with that data set. All right, so all right, so let's do part A. So if you look at part A, it says use the information from the sample to give the best point of estimate of the population parameter. So if you remember the point of estimate, it pretty much depends on what we're trying to do. So for this one, we're trying to find pretty much what's the average age that baby first crawl. So for this one, the point of estimate will be X bar. So what we're gonna go ahead and do, we're gonna go ahead and find what X bar is equal to. And I'm actually gonna use the, what you call it, the TI-84 to help me do this. So if you have the TI-84, you might wanna take it out for that way we could get started. So we're in chapter 9, page 13. All right. So I'm gonna go ahead and enter the data set in here. So I'm gonna go to stats. I'm gonna go to edit because I wanna enter the data set. All right, so I wanna clear this data set. So I'm gonna go all the way up. Once L1 is highlighted, you press clear and enter, and now the whole data set is clear. I'm also just gonna do that for L2. You have to keep it nice and clean. All right, so right now I'm gonna put the data set for how many weeks did it take for the baby to first crawl. So we'll put 52, 30, 44, 35. All right. All right, so I enter all the data set into L1. So for this one, since I want to find what the mean is, to find the mean, I'm going to go to stats. I'm going to move it over to calculate. And I'm going to do a 1-bar stats. So if you look at it, it's asking me where do they want me to look for the data set. So since I enter my data set in L1, I want to tell it look in L1. If I would have put the data set in L2, I would have told it look in L2 for the data set. And the frequency list should always be 0. So let me go over here with calculate. Wait, all right, so the mean is 38.25. 38.25. All right, and that's it for part A. Any question in regard to part A? All right, so let's do part B. So for part B, it says find the standard deviation of the sample. All right, so if you look at part B, you just want the standard deviation of the sample. Technically, we already found that because when I did the one bar stats, it gave me all of these stats. And if you look right here where it says SX, that's my standard deviation of the sample. So if you look at it, it's pretty much just 10. So we're going to say standard deviation of the sample is 10.
So for the standard deviation, we're rounding up.
Well, usually you get like one decimal place, but if you look at what I got like 10.001.
Okay.
So like usually you want like that point something, but if you use a zero to round up to zero, you get zero. So
Oh, okay. So we're not using the 4 decimal places on this one?
now usually for the 4 decimal place, you only do that for when you're dealing with proportional data set.
Okay.
Yeah, but usually when you're dealing with the mean and standard deviation, usually if you get like 1 decimal place, that should be good.
Okay.
What's the symbol below the SX? Isn't that standard deviation?
That is standard deviation, but that's standard deviation of the population.
Ah, okay.
Yeah, so if you look at it, since we only had 12 babies, I'm pretty sure there's more than 12 babies in the world, so that's why you don't want to use the one below it, because that represents that you're telling the calculator you have a population, but we don't have a population, you have a sample of 12. Sweet. All right, so let me go back to my notes. All right, so far for A, I got A X bar is equal to 38.25. I got B is equal to S is equal to 10. So let's go ahead and do C. So if you look at C, C says construct a 95% confidence interval estimate for the mean age at which baby first crawl. So if you kind of look at it, some key things that they're telling you. So the first key thing that they're telling you to construct a confidence interval. So that's the first thing that they're telling you that's important. So that's how I know we're in chapter 9, because they're telling us that we want to construct a confidence interval. So then if you remember, for confidence interval, we technically have 3 different options that we could do. We could do what we did in chapter 9.1, where we construct a confidence interval for the proportion, or 9.2, we construct a confidence interval for the mean, or 9.3, where we construct a confidence interval for standard deviation. In this case, if you look at it, since they're telling us we're doing it for the mean, that's how I know we should be using the information that we got for 9.2 and not 9.1 or 9.3. All right.
We're only on 9.2, right?
Yeah, correct.
Okay.
Yeah, we still haven't started 9.3. We should start 9.3 today, though. All right. So if you remember the formula for margin of error is T alpha divided by 2 multiply by S divided by square root of N. So we're going to go ahead and find margin of error. So S is equal to 10. My N is equal to square root of 12, because there's only 12 babies. And the T alpha divided by 2, T alpha divided by 2, we're going to use the T table in order to find T alpha divided by 2. So just remember, anytime you're getting the T value, you need 2 important things. So the first important thing that we need to find the T value is confidence level. So the confidence level is just the percentage that we want to do the confidence interval for. So if you look at it, they say a 95% confidence interval. So that means our confidence level is 95%. Then you want to find degrees of freedom. So degrees of freedom is n minus 1. So that means it's 12 minus 1, and we get 11. So for this one, we're going to say confidence level is 95%, degrees of freedom is 11. And those are the two information we're going to look for when we go to the t-table. All right. Any question in regard to how I got that before I go over to the t-table? All right, so let's go to the t-table. So degrees of freedom is 11. So that means you select this row over here. So then to figure out which of these number we're going to use, we have to just find the confidence level. So if you look in the bottom where it says confidence level, we're going to use 95% confidence level. So if you look, where do they intercept? They intercept at 2.201. So that's our t-value. So yeah. So we get 2.201 times 10 divided by square root of 12. Any questions so far? How I substituted the t, the s, or the n for the formula for margin of error? Okay, so up next what I'm going to go ahead and do, I'm going to just go ahead and multiply that out on my calculator, and that's going to give me the margin of error. Once we get the margin of error, we're going to just add it and subtract it to the sample mean, and we're done. So let me transfer over to the TI-84. Let me turn it on. So let me clear this. So we get, what did we get? So we get 2.201 multiply by 10 divided by square root of 12. If I go ahead and work that out, you get your margin of error to be 6 point, and you get one decimal place. Well, let's get two decimal place. So we get 6.35. So that's our margin of error. So that's telling us how much room for error we have. So you're telling us our sample mean doesn't have to be exactly off. We could be off by 6.35 of a week, and we could still capture the true population mean. So that's our margin of error. Any question in regard to margin of error? All right, so let me transition back to the notes. For that way we could finish out this problem. All right, so the last thing we're gonna go ahead and do is we're gonna say, was it 38? Yeah. The 38.25 plus or minus 6.35. So just remember the plus or minus just mean you're doing the operation twice. That means you have to subtract the margin of error, and you also have to add the margin of error. So let's go ahead and do, 38.25 minus 6.35. And you get 31.9. If I go ahead and add this, you get 44.6. All right, so that's our confidence. Well, that's our 95% confidence interval for the estimated mean of age at which a baby first crawls. So telling us based off of this confidence interval and based off of the sample size, well, based off of the sample, it's telling us that the mean age or mean amount of week that it take a baby to first crawl should be somewhere between 31.9 weeks all the way to 44.6 weeks. And that's it for that problem. Any question for this last problem? All right, so lastly, what I'm going to go ahead and do, I'm going to show you how to double check this answer by using your calculator. So I'm going to switch over right now to the TI-84. All right, so first thing you want to go ahead and do, you want to go to stats, you want to go to edit, and first thing you just enter all of the data set in here. So you just want to enter all of the data set into L1 or L2, whatever L you want to enter it to. Once you enter the data set into L1 or L2, whichever one, you go to stats, you want to go to tests, and if you remember on Monday, we just used the T interval. So if you remember on Monday, we were using the stats option because the stats option just means I already know the sample mean, I already know the sample standard deviation, so on and so forth. But say if you don't want to find that, you just want to tell the calculator to find that, you could tell the calculator, look under the data, and then tell the calculator, look on L1 for the data set. And then the only thing you have to enter is our confidence level, which our confidence level was 95%. Go to calculate. And if you look at it, you get 31.896, which pretty much the 0.896, you could just round that up to 0.9. And if you look at it, you get 44.6, which is exactly what we got when we did our problem. So you could just double check it with using the calculator. But that's it. Any questions on this last problem?
For the calculator, I'm sorry, did you say we do anything with the frequency level?
Frequency level should be 0. Okay, if you look at this, we don't have a frequency list. So it should be 0. Like the only time you should put frequency is when frequency is something other than 0. But for our case, it's always going to be 0. All right, so let's scroll on down. All right, so what I want you to do, take a minute and do the next problem. And then I'll you put the right answer. And that way you can see if you did it correct or if you didn't do it correct. All right, so let's do this one. So for N, you should have gotten that is 15 because that's how many burners they're testing. For the sample mean, they say the average time that it cracked was at 1,230, and then the sample standard deviation was 270. And then if you look at it, the confidence level is 99%. So if you actually go ahead and work this out, the answer you should have gotten was 1,022.5 all the way to 1,437.5. And that was it for that problem. Any question for that problem? All right. So let's move on to something new. So for this one, we're going to determine the sample size needed. All right, so we're gonna kind of switch over from. So we're gonna switch over from finding the confidence interval. Here, let me go get water. All right, so I'm back. So what I was trying to say, so we're gonna be switching over from finding the confidence interval to finding how big of a sample size is needed if you want to have a certain margin of error, and depending on our sample standard deviation. So for this one, the formula we're gonna be using is Z alpha divided by 2 multiplied by S divided by margin of error. And once you do all of that mathematical operation, you're just gonna square that data set. And just remember the n value should always be rounded up to the nearest whole number, because since n cannot be a decimal, because pretty much n represents how many objects or how many people you have. You can't really have a percentage of a person or a percentage of an object. Either you have the entire object or you don't have the object. Cool. All right, and also just in case you're wondering why we're using the Z value. So the reason why we're using the Z value is because if you kind of remember for the T distribution, in order to find the T distribution, you have to know how big of a sample size you have. Because if you remember, in order to find what the T value is, you have to find degrees of freedom. And the way that you find degrees of freedom is you do n minus 1. So in this case, since we're trying to find what n is, the T distribution wouldn't really work out, because the T distribution relies that I know the sample size. But if I'm trying to find what the sample size is, you don't want to use the T distribution. So that's why we substitute the T distribution with the Z distribution. All right. Any question in regard to the formula before we move on? All right, so let's practice on this first problem. So for this one, says, suppose we wish to conduct a survey to see that the average students, what the average students spend at the bar on a Saturday night. We know from previous research that the standard deviation is $8. we want to see what is the minimum sample size needed to be 80% confident and to be within $2 of the mean. All right, so you kind of also have to remember in chapter 9.1, 9.1, we did something like this, but the difference was when we were doing it for 9.1, we were trying to find what would the proportion data set, and we wanted it to be within a certain amount of that proportion. So if you kind of look at this new example, we're talking about the mean. So that's why I know I want to use this formula versus using the formula that we learned from 9.1. Because for this one, we're trying to estimate what the average amount a student spend on a bar on a Saturday night versus the 9.1 where we're trying to find the proportion. So first thing we're gonna go ahead and do is go ahead and label everything. So the first information that they give us that's relevant is our sample standard deviation, which they tell us is $8. So the next thing that they tell us that's relevant is the confidence level. They tell me a confidence level is equal to 80%. And I'm going to use this confidence level to help me find what Z alpha divided by 2, what that's going to equal to. Lastly, if you look at it, it's telling us it had to be within $2 of the mean. So since they're telling me that's what it has to be within, they're telling me that's my margin of error. So we're going to say E is equal to $2. All right. So far, any questions? I got S, confidence level, or margin of error. All right. So right now, what I'm going to go ahead and do, I'm going to go ahead and use a t-table, and that t-table is going to give me the Z value. So if you remember the confidence level was 80%. So if you look right above 80%, you get 1.28. And just remember right here, it says the Z value. So that's why I'm using this row, because since I want to find what Z alpha divided by 2, all you have to do is look at what the confidence level is, and then you look at the number right above it, and that should give you the Z value. So you get 1.282. Any question how I got the 1.282?
So we would use the Z value anytime we don't know the sample size or N.
Correct. If you're finding the sample size, you're always going to use Z because, like I said, the T distribution, it relies that you know the sample size, but if we're trying to find what the sample size is, you're not going to know what the sample size is. So, yeah. So 1.282. All right, so if you look at it, I already have everything necessary in order to solve for this N. So we'll say N is equal to Z, which is 1.282, multiplied by sample standard deviation, which we found to be 8, divided by my margin of error, which was 2. And we're going to take this to the second power. Any question for any of those 3 substitution? Okay, so let me transfer over back to my calculator. And let me just work it out. So for this one, you do want to use parentheses, because if you don't use parentheses, it will give you the wrong answer. So you do parentheses, 1.282 multiply by 8 divided by 2, close your parenthesis, put it to the second power, and we're done. So if you look at this one, it says we need 26.3. But if you remember, anytime you have a decimal, you round that decimal up to a whole object or a whole person. So we're going to say we need a sample size of 27. And that's it. Any question on why we get N is equal to 27 for this case scenario? Sweet. All right, so let me go back to the notes and we'll do a second problem. In case you're wondering how I wrote it, so I put 26.3, but then you just rounded it up to 27. All right, so for the next one, it says the cheetah is the fastest land mammal and is highly specialized to run down prey. Researchers want to determine how fast the cheetah actually is. From prior studies, they were able to get that the standard deviation speed for a cheetah is 4.2 miles per hour. What is the minimum amount of cheetah they need to sample if the research want to be within 1.2 mile per hour of the cheetah actual speed and have a 99% confidence level? All right, so let's go ahead first, just label everything. So the first thing they give us is 4.2. So the 4.2 just represent our sample standard deviation. All right. So if you look at the next thing that they give us the 1.2 miles per hour. And they say within, so that's telling us that's our margin of error. So it's telling us margin of error is 1.2. And lastly, they give us a confidence level of 99%. So we're going to use the confidence level in order to get Z alpha divided by 2. And if you look at this one, since we're trying to figure out like how fast the cheetah is, essentially you want to find like the average, how on average, how fast is a cheetah. So that's why for this one, we want to go ahead and do pretty much this formula versus using the other formula, because the other formula is for proportional data set. All right. Any questions so far for any of the labeling?
So when we're using our confidence level to find Z alpha divided by 2, previously we would just use that value as all of Z divided by 2. But this one, we're just using that as Z, right? Like
No,
when
no, you're using it for Z alpha divided by 2. Because
Okay.
whatever value you get from the T table, that value is pretty much Z alpha divided by 2.
Got it. Okay, it's not just Z.
Yeah, it's not just Z, it's Z alpha divided by 2.
Perfect.
Okay, so let me go over to the T table. For that way we can find the Z value for a 99% confidence level. All right, so for 99% confidence level is right over here. Oh, wait up. I think this thing froze, so let me stop share, reshare. So you get 2.576 because that's right above the 99% confidence level. So that's the value we're going to use for Z. So we're going to use Z alpha divided by 2 is equal to 2.576. Any questions so far on how we found 2.576? All right, so let's go ahead and just substitute everything in. So we got, what's the first thing that we do? They just do. So we do Z, which is 2.576. You multiply that by standard deviation, which is 4.2, and you divide that by your margin of error, which is 1.2. And then don't forget to square that value. All right. So I'm gonna go ahead, go to the TI-84 and just work this out. All right, so we're gonna say 2.576 multiply by 4.2, all divided by 1.2. And don't forget to do the square. All right, so you get 81.3. So you round that up and you get 82. So you go the sample size that's needed. If you want to have a margin of error of 1.2 mile per the hour and a confidence level of 99%, you're going to need roughly 82 cheetah to sample their speed. All right, but that's it for that second example. Any question for that second example?
Yeah, I have a question. So is the indication that we use this formula, is the mean is not given to us in the problem? Or how would I know to use this formula?
Well, the way that you know to use this formula, let me transition back to the notes. Pretty much, if you look right here in the note, because if you look at it, it says, what is the minimum amount of cheetah they need to sample? So that's kind of telling you you're trying to find the sample size. Because telling you what is the minimum amount of cheetah they need to sample. So they're telling you you're looking for the sample size. And then pretty much you have to figure out, since you're trying to estimate the average speed of a cheetah, pretty much that's why you're using this formula. Because I don't want you to go like, okay, since samples to the sample mean it's not given, I'm gonna use this formula because that might lead you to the wrong conclusion.
Got
But
it. Thank you.
you have to just look for the question, because the question will tell you like how big of a sample size or what the minimum sample size needed. So just look for that.
Thank you.
Yeah, no problem. All right, so let's do this last one. And then we'll move on to 9.3. So it says a researcher wanted to determine the mean number of hours per week, Sunday through Saturday, the typical person watched television. Results from a Sullivan Statistics survey indicate that the sample standard deviation is 7.5 hours. So all this gave me is the sample standard deviation of 7.5 hours. And they also, if you look at it, they tell me that the research want to determine the mean number of hours per week. So we know that we are trying to find what the mean population is. So far, I know we're trying to find the mean population, and they told us that the sample standard deviation is 7.5. So if we look at A, it says how many people are needed to estimate the number of hour the number of hour people watch television per week within 2 hours with a 95% confidence level. So if you look at this one saying how many people are needed, so that's telling us how big of a sample size do we need. So I know we're trying to find N because it's telling us how many people are needed. So it's telling us how big of a sample size should we get. If you look at the problem, it said they had to be within 2 hours. So within 2 hours, that's them telling us the margin of error should be 2. If you look at it, it says we want a 95% confidence. So that means confidence level is equal to 95%. So I'm going to use this to find Z alpha divided by 2. All right. So any questions so far on anything written on the notes? All right, sweet. All right, so I think we're gonna go ahead and do, I'm gonna go ahead and find the Z value. So for the Z value, we're looking if for a 95% confidence level. So if I go over here, 95% is right over here. So if you look at 95%, if we have a 95% confidence level, my Z value is 1.96. So 1.96. Everybody got, I got Z alpha divided by 2 is equal to 1.96. Okay. So since we're trying to find the sample size, we're going to substitute it into the formula for sample size. So we're going to say n is equal to z, which is 1.96 multiplied by s, which is 7.5, divided by margin of error, which is 2, and you square. So for this one, I'm going to do it on my calculator. So also try doing your calculator to see if you get the same answer as me. So you get 1.96 multiplied by 7.5 divided by 2, and you square it. And that will give you 54.0225. You round that up to 55. And that's it for that last problem. Yeah, good, Alan. 55. All right. And that's it for A. Any question in regard to A? All right, let's do B. So for B, it says how many people are needed to estimate the number of hours people watch television per week within 1 hour with a 95% confidence. All right, so if you look at A and you look at B, they're exactly the same thing. They're asking for the same thing. The only thing they're changing is my margin of error. Because if you look at A, we had a margin of error of 2. If you look at B, we had a margin of error of 1 hour. So all we're gonna do, we're gonna get the same formula. Pretty much the Z and the S will stay the same. The only thing changing is margin of error. So for part A and for part B, which one want a more accurate reading? Because if we're doing it within 2 hours or if we're doing it within 1 hour, which one is saying that they want a more accurate reading, A or B?
It would be B, right?
Yeah, it will be B. Yeah, because if you look at B, so it's wanted to be within 1 hour. They wanted to be more accurate. So since B wanted to be more accurate, you're going to be expecting a bigger sample size because kind of think about it, like if you want to be more accurate, that's going to mean you're going to need a bigger sample size. If you want to be less accurate, which B is, you're going to need a smaller sample size. So we should be expecting a bigger sample size. All right, so let me copy and paste this. So the only thing we're going to change is this 2, and we're going to change that to a 1. All right, so if you look at that, you get 216.09, and that's equal to 217. And we're done. And that's it for B. Any question for B? All right, so let's do C. So for C, it says, what effect does doubling the required accuracy have on the sample size? So if you look at B, we have a margin of error of 2. If you look at, if you look at A, you had a margin of error of 2. If you look at B, you had a margin of error of 1. So technically for B, pretty much B is we double the accuracy because we went from an accuracy of 2 hours to an accuracy of 1 hour. So we double the accuracy. So what happened to our sample size once we doubled the accuracy? Did it tell us that we needed a bigger sample size, or did we need a smaller sample size if we double the accuracy?
Needed a bigger sample size.
Yeah, so we'll say yeah, so if we double the accuracy, a bigger sample size is needed because pretty much if you want to get a more accurate answer, that's going to lead us to getting a bigger sample size. So the more accurate we want to be, the bigger sample size we're gonna need in order to be accurate. All right, but that's it. Any question for A, B, or C? All right, so let's scroll on down, and this should be chapter 9.3. All right, so for 9.3, we're gonna do the last confidence interval, and this is confidence interval for standard deviation. So for this one, you're gonna need the other table. So if you remember on Canvas, I put two tables. One of the table was the t table. The other table was the chi-squared table. So for 9.3, you're gonna be using the chi-squared table. Also, the symbol for chi-square, it kind of look like an X, and then they put a square. So this is chi, this is square. So you go chi-square. All right, so let me give you some basic information in regard to chi-square. So let me try to finish it, fit this picture in. All right. So one thing you kind of have to notice, if you look at the drawing that I have here, so this is for different type of degrees of freedom. So this is like for degrees of freedom of 1, degrees of freedom of 2, degrees of freedom of 3, degrees of freedom of 4, so on and so forth. So if you kind of look at the shape that we're getting, you're pretty much getting a data set that's skew right. So that's what the first Roman numeral is saying. It is saying that the chi-square distribution is not symmetric. So we're saying the chi-square distribution is not symmetric because if you look at all of these shapes that I drew out, pretty much none of these shapes are symmetric. Most of them are right skew data set. So that's what the first one is saying, that the distribution of a chi-square is not symmetric. So the second thing is, just like the t-table, the chi-square distribution rely on degrees of freedom. So just remember, degrees of freedom is equal to n minus 1. All right, so the next thing is Roman numeral number 3. It says, as the number of degrees of freedom increases, the chi-square distribution become more nearly symmetric. So if you kind of look at these drawings that I have here, it kind of started looking like, hey, the bigger the sample size get, the more and more it becomes symmetric. So that's what that last one is saying. You're kind of following the law of large number. Like the bigger the sample size get, the more and more it become normal symmetric. And then for the last one, that's really different from the t distribution and the z distribution. If you remember for the z distribution, the t distribution, they're able to be negative and positive. But one thing that the chi-square distribution has that's different from them, that the chi-square distribution, it actually start off at 0 and yet go all the way to positive infinity. So for the chi-square distribution, it start off at 0 and yet go to positive infinity. So for the chi-square can never be a negative value.
So does that mean they're always skewed right? They're never left because that would go to potentially negative.
Well, all of them will start off as skew right.
Okay.
And then, like, depending on the sample size, it might go symmetric. All right, so those are your key facts in regard to the chi-square distribution. So just note, it doesn't start off symmetric, but if you get a big enough sample size, pretty much it will start becoming more and more symmetric. And lastly, just know that the chi-square distribution always start off at 0 and work your way up all the way to infinity. So those are all of the possible things for the chi-square distribution. Any question for the chi-square distribution? All right, so let's go ahead. Frozen. All right, so let's go ahead and look at the formula. So for this one, the point of estimate is still gonna be S. So if I don't know what standard deviation of the population is, for my point of estimate, it's gonna be equal to S. So for this thing is now, since we're trying to estimate what the sample not the sample, but what the population standard deviation is, the best point of estimate for that will be the sample standard deviation. So if I don't know what the population standard deviation is, if I want to estimate what it possibly could be, we're going to use S as a point of estimate. So for this one, I kind of want you to kind of notice it's a little bit different because we're not actually going to have a margin of error in this case scenario. The way that we're actually going to get a two different value is from the chi-square table. Because for the chi-square table, instead of just having one number, you're actually going to be pulling two numbers from the chi-square table. All right, so let's get into the formula. So this first formula, if we're trying to find the confidence interval for variance. So for variance, if you look at it, you have to do n-1, which is essentially just finding the degrees of freedom, and then getting S to the second power. So if I tell you the sample standard deviation is 5, all you have to do is get 5, take it to the second power, and that's how you get that portion. Right. Any questions so far for the top part? And then in order to get this portion right here, this is the chi-square table. Same thing for this fellow over here. In order to get those two, we're going to use the chi-square table in order to attain those two information. So if you look at this problem, the only thing you truly need, you just need to know the sample size, the sample standard deviation, and what is our confidence level. And then pretty much the two bottom number, we'll get those from the chi-square table. And I'll show you how to get those values from the chi-square table. All right. Any question in regard to variance confidence interval? All right, so let's go into the second formula. So if you look at the difference between this formula and this formula, the only thing different is the square root. Because pretty much anytime you have the variance, if you want to make it into a standard deviation, you have to take the square root of it. So whenever you find this, you have to figure out, do you want the variance or do you want standard deviation? If you want variance, do not take the square root. If you want to find the standard deviation confidence interval, that's where you want to take the square root. So you kind of depend, what do you have? So if you know you want to find the confidence interval for standard deviation, just know that you have to take the square root. But if you want to find the confidence interval for variance, you don't have to take the square root. So those are the two formulas. So before we actually get to the formula, I'm going to show you how to get these values in the bottom. So if you have the chi-square table, take it out. So if you have it downloaded on your computer, you just have it handy with you. If you print it out, you have it in front of you. For that, we can kind of see, how do I get the chi-square value? All right, so let's go on down and let's focus on chi-square. All right, so for this one, all we're going to focus on is how to get the chi-square of alpha divided by 2 and chi-square of 1 minus alpha divided by 2. So we're going to do part A. So for part A, they tell me this is an 80% confidence interval, and we have a sample size of 17. So the first thing we're going to go ahead and do is find degrees of freedom. So degrees of freedom, if you look at it, since your sample size is 17, if you do 17 minus 1, you get 16. So that's your degrees of freedom. Any questions so far? I got degrees of freedom of 16. All right. So up next, we're gonna get alpha. So in order to get alpha, you have to just use the formula 1 minus the confidence level. So in this case, you go alpha is equal to 1 minus confidence level of 80%, which is 0.20. So I know alpha is equal to 0.20. Any question I got alpha is equal to 0.20? All right, so let's get to the final step. So if you look at this chi-square, you see how it says chi-square of alpha divided by 2? In this case, where I see alpha, I'm gonna put 0.20. So I do 0.20 here, divided by 2. If you do 0.20 divided by 2, you get 0.10. Because 0.20 divided by 2 should give you 0.10. So the two things I'm going to look for the chi-square table, I'm going to look for something that says chi-square 0.10, and I'm going to look for degrees of freedom of 16. Any question on how I got chi-square 0.10? All right, so let's go ahead and go to the chi-square table. Now, let me download it. Statistical table, chi-square table. All right, so here's your chi-square table. So if you look at the chi-square table, they have this drawing over here. It's right skew. It's kind of remind you it's not symmetric. Okay, so if you remember, I said we're gonna look for two things. We're gonna look for chi-square of 0.10. We're also gonna be looking for degrees of freedom, which I believe was 16. So if you want, you can first look for degrees of freedom. If you look right here where it says DF, that's degrees of freedom. So degrees of freedom of 16 is right over here. So that's how you use degrees of freedom. It tells you which row to select. Next thing I want to do, I want to select the chi-square. So if you look at it, we get chi-square of 0.10, which is this one over here. So any question why I selected that column or that row? So if you look at where do they intercept at 23.542. So that's our answer. So we'll say 23.542, 23.542, 23. All right, and that's how you get chi-square of alpha divided by 2. Any question for chi-square of alpha divided by 2? All right, so up if we're gonna go ahead and do, we're gonna do chi-square of 1 minus alpha divided by 2. So for this one, if you look at, we already know what alpha is, so we're gonna say chi-square of 1 minus 0.20 divided by 2. So that give me chi-square of 1 minus 0.10, which give me chi-square of 0.90. So for this one, instead of looking for chi-square of 0.10, we're gonna be looking for chi-square of 0.90. And we're still gonna be using the same degrees of freedom of 16. So now we're gonna look for chi-square of 0.90, degrees of freedom of 16. Oops, not you. All right, so if you look right here, here go chi-square of 0.90. So if you look at where do they intercept at 9.312. 9.312. Alright, and that's how you get the 2 chi-square value. So pretty much just, and also if you look at it, these two numbers, they complement each other. Because if you look at a chi-square of 0.10, the other one chi-square of 0.90. So these should always add up to 1. So if I already know this one is 0.05, that should automatically tell me this one should be 0.95, because really you don't really have to do all that work. You could just use the complement rule to find that. All right, but any question in regard to A? All right, let's do B. All right, so for B, if you look at it, we get confidence interval in 98% and n is equal to 36. So if n is equal to 36, that means degrees of freedom is 35. So if you do 36 minus 1, you get 35. So up next, we're going to find alpha. So alpha is equal to 1 minus 0.98. So that's 0.02. So we're going to say chi-square of 0.02 divided by 2. Well, that's going to give me chi-square of 0.01. Any question for chi-square of 0.01? All right, so right now what I'm going to go ahead and do, I'm gonna go ahead and look at the chi-square table. I'm gonna look for degrees of freedom of 35. I'm also gonna look for chi-square of 0.01. So let me erase this. All right, so first let's look for degrees of freedom. All right, so if you actually look at the degrees of freedom, there's actually no degrees of freedom of 35. So if you look at it, 35 is actually in between these two numbers. So 35 is exactly in between 30 and 40. So anytime you have this scenario, what you always want to do, you always get the lowest degrees of freedom. So in this case scenario, since 35 is equal distance from 30 and 40, you're going to choose the lower of the two values. So that means we're going to be using degrees of freedom of 30.
So if our degrees of freedom were 36, we would go up to 40.
Correct. But if it's equal distance is always choose the degrees of freedom that the lower degrees of freedom.
Is this a standard table, or is there one that's like more expansive with more degrees of freedom?
No, like this should be the standard table. Like from all the tables that I usually see, it's usually this. It is kind of going that there's not that much of a difference by going like 31 degrees of freedom, 32 degrees of freedom. So they rather just jump.
Got it.
All right. So right now we're good with degrees of freedom of 30. So if we remember correctly, chi-square was actually chi-square of 0.01. So that's all the way over here. So I'm actually gonna have to go pretty far down. So, oops, cross it out. All right, so if you look at where do they intercept? They intercept at 50.892. So that's the value we're gonna actually go ahead and use. So we're gonna use 50.892, 50.892. So that will be our chi-square of alpha divided by 2. So now if I want to find chi-square of 1 minus alpha divided by 2, so for this one, I'm going to use a shortcut. And I say this is chi-square of 0.99. Because if I know the first one was chi-square of 0.01, the next one has to be chi-square of 0.99. Because if I do 0.99 plus 0.01, it adds up to 1. So we're going to look for the column that has chi-square of 0.99. And then we're gonna select those. So here go 0.99. So I select this. Keep on going down. And I get this number in between. So we get 14.953. Let me put that in the chat for I won't forget. 14. Any question? I got 14.953. So yeah, 14.953. And that's it for B. Any question in regard to how I got B?
So when it's asking for the confidence interval, we don't need to do the two numbers within the parentheses. We're just doing the X or the chi-squared calculation, and that's it.
Well, for this one, we can't do the confidence interval because we don't know the S.
Oh, I see. Okay.
Yeah. Like for this one, I just want to show you how to get these two value. But once we actually get to a problem, we'll do the whole thing all together. But for right now, you just purely want to focus on how to get chi-square alpha divided by 2 and chi-square 1 minus alpha divided by 2.
Okay, so this is step 1.
Yeah, so this is just like pretty much step number 1, what the first thing you have to do.
Okay.
The table.
All right, so let's go ahead and do C, and I think that should be good enough. So for this one, for part C, it said confidence interval is 90% and n is equal to 16. So for this one, we get, here, let's do a different color. We'll get degrees of freedom is equal to 15. We get alpha is 0.10. Okay, if you do 1 minus 0.90, you get 0.10. So for this one, we're going to say chi-square of 0.10 divided by 2 is chi-square of 0.05. So right now, what I'm going to go ahead and do, go to the chi-square table, look for degrees of freedom of 15, and get chi-square of 0.05. Any questions so far? I got degrees of freedom of 15 or chi-square of 0.05. Wait. So 0.05, 15. All right, so first we're gonna choose 15. So 15 is here. And then 0.05 is here. All right, so if you look at where do they intersect? Well, they intersect at 24.996. So let me put that in the chat for that way I won't forget. So we'll say 24.996. So we'll say 24.996. And we're all done for chi-square of 0.05. So now we're gonna do chi-square. So remember, is that chi-square of 0.05? That means this is chi-square of 0.95. So we have to look for degrees of freedom of 15, but chi-square of 0.95. So here you go, chi-square of 0.95. So if you look at where do they intercept at 7.261. And that's it for part C. Any question in regard to part C? All right, so let's actually move on to a problem. All right. So for this one, says a simple random sample of size n is drawn from the population that is known to be normally distributed. The sample standard deviation S is determined to be 4. Constructing 90%. But that should say confidence, not condensed. So constructing 90% confidence interval for sigma square and for sigma if the sample size n is 16. So sigma square, that's actually just variance. We actually went over variance like in the beginning chapter of chapter 3, but we really didn't focus on it. So for this one, what we want to go ahead and do, we want to go ahead and find the confidence interval for variance, but we also want to find the confidence interval for standard deviation. So for this one, they tell us our sample standard deviation, S, is equal to 4. They also tell us N is equal to 16. Any questions so far? I got S is equal to 4, N is equal to 16. All right. So if you actually look at this, so we want a 90% confidence interval and we want sample size of 16. So technically we already did that one in part C. So we already got the chi-square value for both chi-square of alpha divided by 2 and chi-square of 1 minus alpha divided by 2. So we already know chi-square of alpha divided by 2 is 24.996. 24.996. And we already know chi-square of 1 minus alpha divided by 2 is 7.261. All right. So chi-square of alpha divided by 2 is equal to 24.996. Chi-square of 1 minus alpha divided by 2 is 7.261. Normally, you have to go to the chi-square table to find that, but since we already did that when we did part C, I'm just using that information from part C. All right. Everybody good? How we got sample standard deviation, sample size, and our 2 chi-square value? All right, so let's go ahead and let's just write down the formula. So for the formula for variance, the formula going to be n minus 1 s squared all divided by chi-square of alpha divided by 2. So that will give me the lower bound. To get the upper bound, we'll do n minus 1 s squared all divided by chi-square of 1 minus alpha divided by 2. So that's going to be the formula for how to get the confidence interval for variance. So all I'm going to do right now is substitute everything in. So if you look at n, we found n to be 16. So we do 16 minus 1 s, which is 4 squared, divided by chi-square of alpha divided by 2, which I found that to be 24.996. All right, so that's the lower bound. So to get the upper bound, we'll do n minus 1, which is 16 minus 1 s squared, all divided by 7.261, because that's our chi-square of 1 minus alpha divided by 2. So far, any question for the substitution? Okay, so I'm gonna go ahead and work this out. So I'm gonna transition over to the TI-84 so that way you can see me work it out. So we'll turn it on. So we'll say parenthesis 16 minus 1. But for this one, it'll really be easier if you do 16 minus 1 in your head and you put 15. So you do multiply by 4 squared and you divide this by 24.996. So we get 9.6. Any question how I got the 9.6? All right, next thing I'm gonna go ahead and do, I'm actually gonna hit the second button and enter. So that way I could get exactly the same thing, because truly the only thing I want to change is the bottom. So you put 7.261, and now you have to delete that 6. I'm gonna hit the delete button, and you press enter, and we get 33.1.
So this is the variance. Don't
Correct.
we need to square these as well to get the standard deviation?
Not square, square root.
Oh, square root, sorry.
All right. So let me go transition over to the note. For that way you can see what I wrote down. All right. So here are my answer. Oh, here is the answer. So that's your answer for confidence interval for the variance. So that's all you had to do for confidence interval for the variance. If I want to do confidence interval for standard deviation, in this case, what you have to do, you have to get the 9.6 and you take the square root of 9.6 and also take the square root of 33.1. So if I take the square root of 9.6, you get roughly 3.1. If I take square root of 33.1, you get 5.8. And this will be your answer if we wanted the confidence interval for standard deviation. So if we want the confidence interval for standard deviation, you have to do an extra step because you have to just find the square root of the answer that you got for the confidence interval for variance. But if you want confidence interval for variance, just don't take the square root, and that'll be it. Any question for that first problem for confidence interval of the variance and standard deviation?
Are we normally going to be asked to find one or the other or both?
Yeah. For most cases, I'm only going to ask you to find standard deviation. Standard deviation is more relevant than variance. Any other questions? All right, let's scroll on down. All right, so let's do this example. So it says find the 95% confidence interval for the variance and standard deviation of the nicotine content of a cigarette manufacturer if a sample of 20 cigarette has a sample standard deviation of 1.6 milligrams. Okay, so a couple of things before we actually start this problem that I want you to notice. So if you look at it, they tell us find the confidence interval, and they told us to find the confidence interval of the variance, but also of standard deviation. So that's how you know you're in chapter 9.3, because we want to find the confidence interval, but we want to find the confidence interval of the variance and standard deviation. So you have to just look for those key words, because like I do have to tell you, find the confidence interval of the proportion, or find the confidence interval of the mean, or find the confidence interval for the standard deviation. And that should be your clue to kind of know, like, okay, if I say proportion, that's 9.1. If I say the mean, that's 9.2. If I say variance or standard deviation, that's going to be 9.3. So you do want to pay close attention to that. All right. So our confidence level is 95%. If you look at our sample size is 20, and our sample standard deviation is 1.6. Everybody good? Confidence level 95%. sample size is 20 and S is 1.6. All right. So let's go ahead and right now we're going to focus on our chi-square value. So we're going to do chi-square of alpha divided by 2, chi-square of 1 minus alpha divided by 2. So first thing I want to find is alpha. So remember, to find alpha, you do 1 minus confidence level, which is 1 minus 0.95, which is 0.05. So that means we're going to do chi-square of 0.05 divided by 2, and then you do chi-square of 0.025. Any question how I got chi-square of 0.025? All right. So if chi-square of alpha divided by 2 is chi-square of 0.025, so that means chi-square of 1 minus alpha divided by 2 should be chi-square of 0.975. And the last thing that I need to know before I go to the chi-square table is degrees of freedom. So degrees of freedom will be sample size minus 1. My sample size is 20. So you do 20 minus 1, which is 19. So right now what I'm going to go ahead and do is look for degrees of freedom of 19, chi-square of 0.025, and chi-square of 0.975 on my chi-square table. So let me transition over to chi-square table. So you have degrees of freedom of 19, chi-square of 0.025, and chi-square of 0.975. All right, so let me put this in the chat for that way I can remember. So it's 32.852. So that's one of the answer, and we get 8.907. So those are my two answers. So we'll go here. So this will be 32.852, and this will be 8.907. So those are my two chi-square value. Any question where any of the two chi-square value came from? All right. So I think I'm going to go ahead and do the formula. So the formula for variance is n minus 1 s squared, all divided by chi-square alpha divided by 2. And then we also want to do n minus 1 s squared chi-square 1 minus alpha divided by 2. So I'm going to go ahead and substitute everything in. So n is equal to 20. So we're going to do 20 minus 1. S is equal to 1.6 squared, all divided by chi-square alpha divided by 2, which is 32.852. So that's going to give me the lower bound. For the upper bound, we'll do 20 minus 1, 1.6 squared, all divided by 8.907. So remember, once I go ahead and calculate this, this will give me the confidence interval for variance. If I want to get the confidence interval for standard deviation, you do have to take the square root of this answer. Any questions so far for what I have in green? Okay, so I'm going to go ahead and transition over to the TI-84. And that way I could just pretty much type it in. So for the TI-84, I'm going to put 19 multiply So I do 19 multiply by 1.6 squared, all divided by 32.852. Press enter. If you look at that, give me 1.48. I'm gonna give one decimal place, so I'm gonna do 1.5. So I'm gonna press second enter. You have to re-enter this information again. Instead of putting 32.852, I'm gonna replace that with 8.907. And you get 5.5. So far, what I have now, I have the confidence interval for variance. So for the confidence interval for variance is going to be anywhere from 1.5 to 5.5. Any question in regard to the last, in regard to that confidence interval for variance? All right, so lastly, what I want to go ahead and do, I want to find the confidence interval for standard deviation. So for standard deviation, all I'm going to do, get 1.5, take the square root of it. So you do radical 1.5, and you get 1.2. You do radical 5.5, and you get 2.3. And that'll be your confidence interval for standard deviation. So all you had to do, get 1.5, take the square root of 1.5, you get 1.2. If you take the square root of 5.5, you should get 2.3. All right. Any question for that last problem? All right, so let's scroll on down. All right, so there was supposed to be a picture on it, but I accidentally I didn't give it the right direction, so it didn't turn out the picture. Oh well. So let's do this next problem. So it says one way to measure the risk of a stock is through the standard deviation rate of return of the stock. The following data represent the weekly rate of return in percent of Microsoft for 15 randomly selected week. Compute the 99% confidence interval for standard deviation risk of Microsoft stock. So these are the percent. So pretty much 5.34, that's a percentage. So that means they gain money. If they lost money, they'll have a negative to it. So if you look at it, they don't give me the sample standard deviation, but since they gave me the data set, I could find the sample standard deviation from this data set. So right now what I'm going to go ahead and do, I'm going to enter this data set into the calculator for that way it could give me the standard deviation of this data set. Because if you look at it, it said compute the 99% confidence interval for standard deviation. So I know I need sample standard deviation for this one. All right, so let me transition over to the TI-84. So we'll go to stats, we'll go to edit. I'm gonna press up, clear, enter. So I'm gonna enter all of these numbers. So we'll say 5.34, 9.63, negative 2.38, 3.54, negative 8.76, 2.12, negative 1.95, 0.27, 0.15, 5.84, negative 3.9, negative 3.8, 2.85, negative 1.61, negative 3.31. All right, so I enter in all the data set into L1. Since I already entered all the data set into L1, I'm gonna calculate the sample standard deviation. So we're gonna go stats, calculate 1 bar stats. I have all my data set in L1, so you leave it as L1. Frequency list should be left alone. Go to calculate. And remember, since this is a sample, you want to use a sample standard deviation of 4.7. So we'll say S is 4.7. Everybody get how we get sample standard deviation of 4.7? All right. So let me go ahead and switch over to my notes. All right, so for this one, what we want to go ahead and do, we're going to jot down some stuff that they give us. So one thing that they give us sample size. They tell us we have a sample size of 15. Also, if you count all of these numbers, they should add up to 15 numbers. So that's the other way you could have done it. They also tell us we're doing a 99% confidence interval. So we know confidence level is 99%. So that means alpha is 0.01. Any questions so far? Anything I have in green? All right, so if you look at the problem, they just want to know the confidence interval for standard deviation. So we don't have to do this for variance. We just have to do this for confidence interval of standard deviation. So the first thing I'm going to go ahead and do, we're going to go ahead and find alpha. Oh, sorry, chi-square. So we're going to find chi-square of alpha divided by 2, which is chi-square of 0.01 divided by 2, which is chi-square of 0.005. So we have to see what does chi-square of 0.005 add up to or equal to. So now if we have chi-square of 1 minus alpha divided by 2, that will is equal to chi-square of 0.995. So right now we're gonna go ahead and look for chi-square of 0.005 and chi-square of 0.995. And just remember for this one, the degrees of freedom, since n is equal to 15, degrees of freedom should be 14. Any question in regard to the chi-square? Okay, so let me go ahead and move over to our chi-square table. So we have degrees of freedom of 14. We have chi-square of 0.001. Well, sorry, 0.005, which is all the way over here. We also have chi-square of 0.995, which is all the way over here. So if you look at it, we get 31.319. So let me just put that in the chat so that way I'll know what it is. And we also get 4.075. All right, so those are my two chi-square values. So chi-square alpha divided by 2 is 31.319. For chi-square of 1 minus alpha divided by 2, that should be 4.075. So let me go ahead and label that. So we'll say 31.319, and we get 4.075. Any question in regard to that chi-square value? All right, so let's get to the formula. So for the formula this time, since we're doing for confidence interval for standard deviation, we start off with the square root. So we do n minus 1 times s squared, all divided by chi square alpha divided by 2. And to find the upper bound, we'll do n minus 1 chi square, s square, divided by chi square 1 minus alpha divided by 2. So all I'm going to do is go ahead and substitute everything in. So we'll do this in black. So it's a square root of n, where n in this case is 15. There you go. 15 minus 1s, which is 4.7. You square it. You divide this by chi-square alpha divided by 2, which is 31.319. And then for the upper bound, you do 15 minus 1, 4.7 squared, all divided by 4.075. Any questions so far how I substituted in and got anything in black so far? Wait. So you go 14 times 4.7 squared divided by 31.319. So we get 3.1. There you go, 4.0750. And you get 8.7. And that's your confidence interval for the standard deviation. Any question for that last round? All right, so let's do the final problem on chapter 9. Okay. So for this last problem, you kind of have to go back to the definition of what is standard deviation. So standard deviation is telling us pretty much how consistent a machine or a number is. So for standard deviation, the closer it is to 0, that's telling us is very consistent. If something is further away from 0, that's telling us it's not consistent. So you kind of have to just remember what the standard deviation represent. It represent how consistent are we getting that number. If you keep on getting the same number over and over again, you should be getting a standard deviation close to 0. But if all of your numbers are different and vastly different, then you should start getting a deviation further away from 0. So you do have to kind of remember that concept about standard deviation. Like the closer it is from 0, the more consistent it is. The further away from 0, the less consistent it is. All right, so you're gonna need that for this next problem. So for this one, it says Coca-Cola is wary that their machine are getting too old and they're not consistent. They randomly select 15 bottles of Coca-Cola and got a mean of 16.95 ounces with a standard deviation of 0.67 ounces. Assume the population is normally distributed. All right, so far we just write down what's given to us. So the three things that's given to us, n is equal to 15, x bar is equal to 16.95, and lastly that s is equal to 0.67.
I think you need to reset. We can't see what you're writing.
Oh, okay. That's weird. Thank you, Anna. So let's reshare. Yeah, so n is equal to 15, x bar is equal to 16.95, s is equal to 0.67, He also told us this is normally distributed, so all of that is good. All right. Everybody good so far for those notation? All right. So if you look at part A, it says constructing 95% confidence interval for the population standard deviation. As soon as you told me we're doing a confidence interval for population standard deviation, pretty much X bar is useless to us. Okay, if you look at the formula has no need for X bar. So since we're doing a confidence interval for population standard deviation, we don't need X bar. All right, so for this one, they tell us we're doing a 95% confidence interval. So if we're doing a 95% confidence interval, that means alpha is equal to 0.05. And we have a degree of freedom of 14. So remember, since we're doing 95% confidence interval, that means confidence level is 95%. So if I want to find alpha, do 1 minus confidence level. So that will give you the 0.05. So up next, I'm gonna go ahead and do chi-square. So remember, we want to find what chi-square of alpha divided by 2 is, but we want to find chi-square of 1 minus alpha divided by 2 is. So for chi-square of alpha divided by 2, we'll do chi-square of 0.05 divided by 2, which you should get chi-square of 0.025. So if we get chi-square of 0.025, that means chi-square of 1 minus alpha divided by 2 is chi-square of 0.975. Any question on where to that, how I got those chi-square value? All right, so up next, we're gonna go ahead and do, we're gonna go ahead and find what do those chi-square value, what are they equal to? So we're looking for 0.025 and 0.975, so I have to use my chi-square table. What was the sample size? All right, so we get 14 is our degrees of freedom. We get 0.025, and we also get 0.975. So let me just write that down on the chat for that way I can remember those numbers. So you go 26.119, and then you get 5.629. Right, so those are the two values I get for chi-square. Any question on how I get those two values? All right, so let's go back to the thing. So let me just write those out. Here, we'll do this in black. So we'll say 26.119 and 5.629. All right, so object what I'm going to go ahead and do, since I want to find the confidence interval for population standard deviation, I'm going to go ahead and just substitute this right into the formula. So we're going to say n minus 1, which is 15 minus 1, s squared, which is 0.67 squared, all divided by the biggest number, which is chi-square alpha divided by 2, which is 26.119. So I do the same process again. So you do 15 minus 1, you get 0.67 squared, all divided by 5.629. So far, any question on any substitution that I made so far? All right, so I'm gonna go ahead and calculate this. So you get 0.49. And you get 5.6. You get 1.06. And that's how you get the confidence interval for standard deviation. Yeah. And also, in case you're wondering if the TI-83 could do that for you, no, it cannot do. This is the one function that the TI-83 or 84 doesn't have. So for this one in the test, you do have to pretty much find the chi-square value and just pretty much do the process that we just did right now. All right, but that's it for A. Any question in regard to A? All right, let's do B. All right, so if you look at the confidence interval is telling us the population standard deviation could be anywhere from 0.49 ounces all the way to 1.06 ounces. So we have to use that for part B. So it said if the standard deviation is 1 ounce or more, Coca-Cola need to replace all the machines. Looking at part A, confidence interval, should they consider replacing all of their machine? Explain why or why not. So for this one, should Coca-Cola replace all of their machine? Because if you look at the confidence interval is telling us the standard deviation for the machine could be anywhere from 0.49 all the way to 1.06. So should they consider replacing all of their machine?
No, because it's less than an ounce.
But are all of the possible options less than an ounce?
Oh, since it can be more than an ounce, we have to consider that.
Yeah, 'cause if you look at 1.06, so that means the standard deviation could be 1.01, or it could be 1.02, or it could be 1.03. So if Coca-Cola is worried that if the standard deviation is above 1 ounce or 1 ounce or more, they should replace all of the machine because the confidence interval is telling us that is a possibility. It is a possibility that the standard deviation could be more than 1 ounce. So for this one, we'll say yes, since the So, but yes, since the confidence interval tell us that it is possible for the standard deviation to be above 1 ounce. And that's it for the last problem. Any question for the last problem? Sweet. All right, so if you notice, we're all done with chapter 9, so that means you're gonna have a test. So what's gonna happen for next weekend? Next weekend, you're gonna have your test on chapter 7, chapter 8, and also chapter 9. So for this weekend, I'm gonna put a study guide on all the topics that will be on the test, but it shouldn't be that hard to do. So yeah, so for this weekend, I'm gonna put a study guide on all the topic to study for your test, which will be next weekend. And also, so that means there's not gonna be a quiz this week on Monday. So there's not gonna be a quiz on Monday. But for next week, we can't really just hold on to the test. So we're gonna start moving forward on next week. So for the first 30 or 45 minutes, I'll let you ask questions in regard to the test. But after that, we're gonna get started with chapter 10. All right. Any question in regard to what I just said or anything?
So what's the date of the test?
Next weekend. Here, let me get my phone. Let me check the calendar.
Is it going to be a Sunday one again?
Well, Saturday to Sunday. All right, so today. So yeah, so the test will be on Saturday, May the 16th to May the 17th. Yeah, good. Yeah, May 16th to May 17th.
And then we have test 4 and then the final, right?
Yeah, so hopefully we'll get to test 4. If not, oh well. But yeah, we should be having test 4 and then the final. All right, any other question?
Yeah, I was hoping to ask questions about the quiz and office hours, but I see that the quiz answers are still hidden. Are they going to remain hidden, or are we going to be able to see them?
No, I'll put it up right now. Here, I'll do this right now.
Thank you.
So we don't have any quiz on Monday, right?
Nope.
Monday is 11, right? No quiz.
Yeah, no quiz on 11.
Yeah. So the May 17 will be chapter 9, 10. Sorry, 8, 9, 10 for the test, right?
No, 7, 8. It will be 7, 8, and 9.
9, May 17, right?
On the what?
May 17.
Yeah, May 16th to the May 17th.
Okay. This will be the exam 3, right?
Yeah, this will be exam 3.
Yeah. Okay.
All right, Anthony, the what you call it? The what you call it? The answer for the last quiz, this should be up now.
Thank you.
Oh, you're welcome. Any other question? Very cool. So pretty much that's it for me. If you do have any questions, what I'm gonna do, I'm gonna just log out of this and then just go back to office hour. So if you do wanna ask me any more questions, I'll be at my office hour in a little bit. So that's why also for all the mother, happy Mother's Day for you this Sunday. It's probably not gonna be the best, but you'll make it work. All right, have a good one. Bye guys.
Bye.